Hi everyone, thank you for your interest in our work, fork graph, cache-efficient fork processing pattern on large graphs. This paper is co-authored by Shengliang Lu, Shixuan Sun, Yuchen Li, Jones Paul, and Bingsheng He. First of all, we've noticed that there is a common pattern in many graph applications, such as between and centrality, network community profile, and landmark labeling. This common pattern is that these applications will select a set of vertices from the graph as the source vertices, and then process independent and homogeneous query from these source vertices. We name this pattern as the fork processing pattern. And these independent queries are then called FPP queries. Each FPP queries could be a single source vertex path for between centrality, or a personalized page rank for network community profile, so and so on. We use the network community profile application as an example to explain FPP. NCP approximately shows the best conductance value for clusters of different sizes in the graph. A previous work published in VLDB 2017 leverages LiGraph to compute NCP by running 100,000 personalized page rank from randomly selected source vertices. The programming logic is given below. We first have a loop that runs for 100,000 times. In each iteration, we randomly pick up a vertex as the source vertex, set the total number of workers as the number of available processors, and then launch LiGraph's compute kernel to compute personalized page rank from vertex V. As existing graph processing systems like LiGraph are designed for single queries, they leverage the intra-query parallelism and show good performance by executing the query one by one. As those FPP queries are independent, we can leverage the inter-query parallelism and execute more than one query simultaneously. The extreme case is that we allocate one thread for each query. So in this piece of code, we first set the total number of workers as the number of processors, and then we use a parallel for loop to fire multiple queries simultaneously, and each query is only assigned with one worker. According to our performance evaluation, the inter-query parallelism shows a better performance for most of the cases. It is because of two reasons. First, it eliminates costly synchronization among threads as threads are executing independently. Second, it increased the memory parallelism by mitigating data dependencies caused by the graph structures. However, we also observe that there is a drawback of inter-query parallelism. Although it performs better than on handling FPP queries, there is a huge rise of the cache miss ratio. The last level cache miss ratio has risen from 30% in intra-query parallelism to more than 80% in inter-query parallelism. The reason is that as many threads are processing different parts of the graph, they are filling cache in an uncoordinated manner, which causes high cache thrashing. These uncoordinated memory accesses limit the benefits of inter-query parallelism. As given in the illustration here, 3 queries are executing by 3 different threads. As the threads are working on different parts of the graph, they are likely to fetch graph data to the last level cache and evade graph data used by other threads, which cause a significant cache thrashing. In this work, we aim to accelerate the processing of FPP queries as it is the major bottleneck for most of the FPP applications. We propose a buffered execution model to address the high cache miss ratio in leveraging inter-query parallelism. Essentially, a buffered execution model leverages the locality and sharing opportunities among FPP queries. Let's suppose there are 2 queries, Q1 and Q2, executing in a given graph. We first divide the graph into LLC-sized partitions. Here, we divide the graph into 4 parts for demonstration purpose. And then we associate each partition with a buffer to store operations generated during processing of Q1 and Q2. An operation is basically the processing status and it updates to the query-specific data by reading the graph data. We then dynamically schedule a partition whose buffer is not empty, and then process the buffer operations within this partition in batch, so that the accesses to graph are expected to be in cache. In the figure below, we first process query 2 in partition 3. The operation expanded will be sent to partition 1 and 4. The operation sent to other partitions will not be processed until the destination partition is scheduled. After processing partition 3, we then schedule to process the buffer operations in partition 1, which stores the initial operation of Q1 and an operation as the subquery of Q2. The newly generated operations are then sent to buffers of P2 and P4. This is the basic idea for buffered execution model. The major benefit of this model is that the query execution within a partition will also be cache-friendly. To efficiently support the buffer execution model, we essentially studied the following two questions. Given a scheduled partition, how to efficiently handle buffer operations? Second, how to schedule the processing of graph partitions. In this paper, we major focused on two parts, intra-partition processing and inter-partition scheduling. We'll now talk about the first one. For intra-partition processing, since we only process operations within cache, the work efficiency becomes essential. For intra-partition processing, we compare two ways of execution. One is to assign all workers to an operation and handle one operation at a time. The other one is to assign an operation with one thread and then process these operations simultaneously. The differences can be visualized in the figure here. The sequential execution is more preferred as it can leverage work-efficient sequential algorithm, and it has little overhead of synchronization and scheduling of threads. As we've discussed previously, that inter-query parallelism shows better performance than the intra one. However, we notice that the sequential execution still requires locking and atomic operations. When threads simultaneously read and write query-specific data, this could potentially limit the performance gain. Therefore, we propose a consolidation optimization to gather the operation based on the query they belong to. At any point of time, only a single thread will be assigned to process operations of the same query so that we can process the operation in an atomic-free manner. Moreover, as the query-specific data is stored in a contiguous space, it avoids stream memory access to data of other queries. Next, we briefly talk about our inter-partition scheduling. Basically, inter-partition scheduling is the outer loop of the intra-partition processing. It answers the following two questions. When should we terminate the processing of a partition and switch to the next one? And then, which partition should be selected to process next? We'll talk about the heuristic-based yielding to answer the first question. In a baseline design, the process should finish processing all operations before terminating the partition, because this will maximize the reuse of cache content. However, we notice that this exhaustive execution leads to local optimal results within a partition, which brings a significant amount of redundant work in the global view. Therefore, we propose to early terminate the processing of operations in the partition based on two heuristics. The first is that as the number of edges processed in the partition is greater than a threshold, the query should yield. The second is that the changes of values within a partition is greater or smaller than a threshold, the query should yield. The processing of a partition terminates when all the query within the partition terminates or yield. And then the yielded process will be resumed when this partition is rescheduled. This is similar to the concept of yield in the process scheduling in operating systems. When we resume the processing of a partition, Some newly propagated operations stored in the buffer could potentially carry better results, which can then be used to prune the leftovers after previous yielding. Therefore, the yielding operation could help reduce the redundancy. In this given example, suppose we are executing single source shortest path started from vertex A. In the baseline approach, the distance of A to E will be processed and updated as 0 to 4. As B and E have outgoing edges, they update partition 2 with 3 operations. We notice that 2 out of the 3 operations are very useless, and the new paths A to D can be used to update the value of vertex E again, so that the processing of E previously is useless. Such an optimal value of E could generate other non-optimal values, which is very inefficient. In figure B, we use the process in partition 1 and at the edge H to E. It then stores the unprocessed status in the buffer of current partition and only send one operation to partition 2. It will eventually get the same correct results as figure A. However, without getting too deep in the local optimal, yielding can help a lot in reducing the redundancy. The next question is, when we terminate a partition, which one should we process next? The most cache-friendly way is always select the partition with maximum number of buffer operations. However, we notice that such a wrong execution order of partition could cause repeated revisit, which cause redundant work and high cache flushing. Our goal is to select a partition that helps the processing quickly converge. We then propose a priority-based scheduling to give such partitions with higher priorities. The priority of a partition is the highest priority value among all the operations buffered in the partition. Operations priorities are generated by a priority functor provided by the user. For example, in landmark labeling, the FPP queries are single source shortest paths. Therefore, the priority functor is just checking with which operator is carrying a shorter path. We propose a priority-based scheduling to give such operations with higher priority. The priority of a partition is the highest priority value among all operations buffered in the partition. Operations priority are generated by a priority functor provided by the user. For example, in landmark labeling, the FPP queries are single source shortest paths. Therefore, the priority functor is just checking which operation is carrying a shorter path. This priority-based method is simple and effective. Besides, in the complete version of this paper, we give the theoretical proof that the processing of FPP query is work efficient, as its work is a constant factor to the time complexity of the best known sequential algorithm. Finally, we built this prototype fork graph based on LiGraph. Besides LiGraph's excellent programming interface, we also expose yield and priority functors that allows user to program. We also have pre-built fundamental algorithms like BFS, SSP, and many others. We evaluate fork graph on a 10-core workstation. The LLC size is 13.75 megabytes. We use A graphs and partition them using Mantis. We compare the performance of fork graph with LiGraph, Gemini, and Graphit using 3 applications mentioned before. LiGraph, Gemini, and Graphit are all executed under both intra and inter-query parallelism. Overall speaking, fork graph shows more than 30 times speed up on average over the other system. And it shows low latency in handling graph analysis tasks. For example, it takes fork graph 42 seconds to finish network community profile analysis on live journal graph, while LiGraph requires more than 20 minutes. The buffer requires additional more space, and fork graph only use 5 to 19 more memory than other systems. In our detailed analysis, ForGraph shows up to a factor of 100 reduction of the number of LLC misses, and it only presents 5 to 16 times more edges than the sequential single-threaded implementations, while other systems possessing several orders of magnitude more edges. These results validate that ForGraph is both cache efficient and work efficient. We have also listed down other experimental results from the paper. ForGraph reduces memory store from 34% to 20%. And it achieves 7 to 8 times speedups when scaling from 1 to 10 cores, which is much higher than other graph processing systems. It can remain high throughput with even growing number of queries. Besides, we also evaluate the effects of the size of the partition. And we noticed that the LLC size partitions achieve the best performance for most of the cases. In summary, FPP is common and costly. Existing solutions show high cache miss ratio when leveraging inter-query parallelism. Therefore, we propose a buffered execution model to coordinate the access to graph partitions. Our system's ForGraph can achieve up to 2 orders of magnitude performance compared to other graph processing systems. As future works, we plan to extend ForGraph to support heterogeneous queries, to support out-of-core processing, and maybe on coprocessors as well. Here is the list of reference dimensions in this presentation. Our source code is publicly available at the URL shown here. Thank you so much for your time.